What is an open fan engine? Is it really any different from a turboprop? And how can it possibly be considered to replace turbofan engines on airliners? If you've ever been frustrated when being told an open fan engine flies faster than a turboprop because that's what it was designed to do, when you really wanted to know how it achieves that, then this video is for you. An open fan, also called an unducted fan or Propfan, is the love child of a turbofan and turboprop engine. Two engine types developed in parallel, each complementing what the other lacks. Open fan designs have already demonstrated 86% propulsive efficiency at Mach 0.78 and are capable of even more. To put that in perspective, this matches or exceeds turboprop efficiency levels, but at speeds 50% faster. It also offers 20% better fuel efficiency than today's turbofans. But to understand why the open fan exists at all, we need to cover some fundamentals while considering the evolution of gas turbine engines in aviation. The world's first production turbojet was the Junkers Jumo 004, powering jets like the Me-262 toward the end of World War II. The turbojet was a brilliant new technology, and the writing was on the wall for high-power piston engines immediately. But the turbojet itself didn't last long. Turbojets were terribly fuel inefficient, especially at lower speeds. The answer to this was the turboprop engine, which appeared about 5 years later, not to replace turbojets, but to complement them. Since a turboprop is essentially a turbojet spinning a propeller, it excelled where turbojets struggled. Turbojets were ideal for fast airliners like the Devil and Comet and supersonic jets like the F4 Phantom II. Turboprops were better for short takeoff and landing transports like the C-130 and airliners like the Vickers Viscount, which operated at lower speeds and altitudes. Turboprop-powered aircraft typically max out around Mach 0.5 and fly at lower altitudes, making them ideal for short-haul flights. They also aged well and remain popular today on aircraft like the ATR-72. Turbojets, however, for all intents and purposes went extinct, lasting only about 15 years before turbofans replaced them for virtually all manned aircraft applications. The turbofan addressed the shortcomings of the turbojet while retaining its advantages for high-speed and high-altitude flight. Unlike turbojets, which produce all thrust from their exhaust, turbofans generate much of their thrust from a large fan up front. This improves both fuel efficiency and takeoff performance through bypass air that enters the nacelle but bypasses the engine core entirely. The thrust principle here is important and is directly responsible for the existence of the open fan engine. A turbojet accelerates a small mass of air to very high velocity. This is inefficient because the greater the difference between exhaust velocity and aircraft velocity, the lower the propulsive efficiency, meaning more engine power is needed to produce the same thrust. Early turbofans had low bypass ratios, but the target quickly became higher bypass ratios for better fuel efficiency. Modern turbofans like the Pratt & Whitney PW1100G used on the Airbus A320neo have bypass ratios of 12.5 to 1, meaning for every 1 kg per second of air entering the core, 12.5 kg per second bypasses it. High bypass turbofans cruise efficiently up to around Mach 0.8, above which they encounter the same compressibility problems that limit open propellers. Modern supersonic jets like the F-35 use low bypass afterburning turbofans that can fly much faster, but at the cost of fuel efficiency. Throughout this evolution, turboprops maintained their niche, perfectly complementing turbofans. The reason turboprops are so efficient at lower speeds is their massive bypass ratios, which can easily exceed 50 to 1, far higher than any turbofan. The slow-spinning propeller accelerates a larger mass of air more gently, which is inherently more efficient. So why not use turboprops on all airliners then? Well, the limitation is blade tip speed of unducted propellers, resulting in lower cruise speeds. When tip speeds approach the speed of sound, compressibility effects cause shock waves and dramatically increase drag, crippling propulsive efficiency. On the ground, it's easy to keep propeller RPM at efficient speeds, but in flight, the aircraft's forward speed adds to tip speed. Since propellers move through the air in a helical path, both rotational and forward speed contribute to tip speed. Constant speed propellers help by increasing blade pitch as airspeed increases, which increases loading and reduces RPM. But this only delays the problem, it doesn't eliminate it. So there exists a hard upper limit around Mach 0.5 for efficient turboprop operation. Turbofans solve this with a duct around the fan. The duct delays compressibility effects by interfering with shockwave formation, allowing blade tips to travel much closer to or even beyond the speed of sound relative to local airflow. The duct also reduces tip vortex drag, guides airflow, allows pressure confinement behind the fan, and provides significant noise suppression. Since the duct enables higher tip speeds, it indirectly enables efficient flight at much higher speeds than open propellers. Turbofans are clearly superior for high altitude, high speed flight, and it's no surprise why ducted turbofans are so popular. But we've reached a point where further efficiency gains create new penalties. To keep improving turbofan efficiency, we need higher bypass ratios so we can accelerate more air per second at lower velocities. But this requires larger diameter fans and thus larger engine cross sections. Not only is physical clearance under the wing becoming problematic, but the duct becomes disproportionately heavier as fan diameter increases. The weight of the cowling doesn't scale linearly, it increases faster than diameter does. We are nearing a stage where the weight penalty of increasing fan diameter no longer delivers acceptable efficiency gains. The duct that initially solved the tip speed problem is now limiting further progress. So engineers began asking, what if we removed the duct? An open fan engine could have a larger diameter and achieve bypass ratios many times higher than turbofans. General Electric claims their RISE engine's bypass ratio will exceed 5 times that of advanced turbofans. And industry bypass ratio estimates range from 40:1 to 75:1, depending on measurement methodology, all without the exponential weight penalty of the duct. But this requires solving the blade tip speed problem that the duct originally addressed. And there is a solution for this, and that is aggressive blade sweep. Blade sweep, the downstream curvature of blades as viewed from the front, is one way to mitigate the tip speed problem. Traditional propellers have mostly straight blades with minimal sweep. So how does sweep help? If a propeller turns at 2000 RPM, the tip travels at the same absolute speed regardless of sweep. However, sweep allows the blade to cut through the air at an angle rather than meeting it perpendicular to its leading edge. This reduces the velocity perpendicular to the blade's leading edge, which is what actually causes compressibility effects. There is a formula to calculate the effective Mach number a swept blade experiences, which I won't bore you with, but this part represents the local blade angle, and you'll see it in effect reduces the contribution of rotational speed. The higher the sweep angle, the lower the Mach number. It's the same principle behind swept wings on jets. Sweep delays the onset of transonic drag. Sweep also weakens the shock waves that form at high tip speeds. Straight blades create strong, abrupt shocks, while swept blades delay shock formation and produce weaker shocks, improving efficiency and reducing noise. A third benefit is reduced tip vortex intensity when combined with blade taper. This decreases induced drag losses. Modern turboprop propellers already use moderate sweep, but competing with turbofans at high cruise speeds requires more aggressive sweep. So, why doesn't all propellers have aggressive sweep then? Well, because it's a trade-off, not magic. Centrifugal forces cause outward tension, and aerodynamic forces create geometric torsional bending, forces that barely exist on straight propellers. So aggressively swept blades requires much stronger blade construction. Sweep also increases span-wise airflow along the blade, which reduces effectiveness at low speeds, like during takeoff and climb, where the compressibility benefits of sweep aren't needed anyway. So we don't by default want maximum sweep on all propellers. Highly swept blades are not desirable for most turboprops, but they're essential for open fan engines competing with turbofans at high speeds. However, even with aggressive sweep solving the tip speed problem, open fans without ducts miss out on certain advantages, like pressure recovery and reduced tip vortex drag. So, to achieve the promised efficiency gains over turbofans, aggressive sweep alone is not enough, and open fan engines need additional innovations. And there are 3 main ways to achieve this. Before going further, you'll hear me use the terms propeller, fan, and rotor interchangeably. At the level we're exploring, they're doing the same job, so there is no need to get hung up on terminology. I did cover the differences in detail in another video, linked in the description. One often overlooked propulsive efficiency loss is swirl. Propellers don't move air backwards in a straight column. They impart a corkscrewing motion to the slipstream. Swirl is the rotational component of momentum. While it contains kinetic energy, only the axial component contributes to thrust. So, some engine power is wasted on swirl instead of thrust, reducing efficiency. One way to reduce swirl is by using anti-swirl vanes, also called swirl recovery vanes. On open fan engines, these look like a stationary row of blades behind the main fan. Air exits the fan at an angle and heats these vanes, which redirect it predominantly backward. Now, most of the momentum is axial, preventing efficiency loss. The result of de-swirling the air is that less power is required to produce the same amount of thrust, improving efficiency. Most turbofan engines also incorporate stator vanes behind the fan for the same reason. These vanes also act as diffusers. They decelerate the airflow and convert velocity into static pressure, which also improves efficiency. This is where the term open fan really starts to make sense. These engines are arguably more closely related to turbofans than turboprops. An open fan is essentially a turbofan with the duct removed and the fan blades redesigned to operate without it. Another way to reduce swirl is contra-rotating propellers. 2 propellers spinning in opposite directions, mounted coaxially on the same shaft axis. Air exits the first rotor with swirl. The second rotor, spinning in the opposite direction, works against this swirl tendency. By countering the rotational motion, the second rotor lessens energy wasted in swirl, instead converting that energy into additional useful thrust. The airflow behind the second propeller isn't perfectly axial, but contains less swirl than a single propeller system. This improves efficiency similarly to anti-swirl vanes, though comparing the 2 approaches is quite complex. A contra-rotating setup needs roughly twice the shaft horsepower since it's driving 2 rotors instead of 1. You could use smaller rotors to reduce the power requirement, but smaller rotors are inherently less efficient as they must spin faster to produce the same thrust, which works against the efficiency gains we're trying to achieve. So comparing efficiency between single rotor with anti-swirl vanes to contra-rotating rotors depends heavily on specifics like rotor sizes and power available. For the same power, A single rotor with vanes is likely more efficient per unit of power. But if you have double the power available, contra-rotating gives you nearly double the thrust while producing only marginally more nacelle drag. In practice, both configurations achieve similar efficiency levels. However, as you'll see later, single rotor with anti-swirl vanes appears to be the preferred design on modern open fan engines, likely due to lower mechanical complexity, reduced manufacturing costs, and more flexible engine placement options. The third efficiency advantage is variable pitch blades, something turboprops have, but turbofans don't. For optimal takeoff performance, a fine pitch angle is needed. This reduces blade loading, allowing high RPM and maximum thrust at low airspeeds. But at high cruise speeds, fine pitch becomes inefficient. A coarse pitch angle is required to maintain proper blade angle of attack relative to the faster airflow. With fixed pitch blades like on a turbofan, you must compromise, and it's typically optimized for fast cruise while accepting reduced efficiency at other flight phases. Variable pitch solves this. As the aircraft accelerates, a governor automatically adjusts blade angle to maintain optimal propeller RPM. This means the propeller operates at peak efficiency during takeoff, climb, and cruise, something turbofans cannot achieve. The anti-swirl vanes also use variable incidence angles, adjusting to match different flight conditions and maintaining efficiency as airspeed and power settings change. Why did 1980s open fan designs mount rotors at the rear of the engine, while modern designs use a tractor layout like turboprops? Well, it's simply a design choice with trade-offs. At the time, it was envisioned that these Propfans, which were the Pratt & Whitney Allison 578DX and General Electric GE36, would be mounted at the rear of the fuselage, while modern designs like the CFM Rise engine seems to favor underwing mounting. Each has advantages. Busher rotors provide more uniform airflow into the engine core, since the inlet isn't affected by rotor wake, but the rotor itself operates in disturbed air from the nacelle, reducing rotor efficiency. Tractor rotors get clean, undisturbed airflow for better rotor efficiency, but create swirling, non-uniform flow into the engine core. So engine placement is the deciding factor. For underwing mounting, tractor configurations are preferred, even though the high-velocity prop wash flowing over the wing increases drag and creates aerodynamic interference. Open fans produce faster slipstreams than turboprops, making this wing interference more significant than on conventional turboprop aircraft. In addition, underwing mounting creates a problem with ground clearance. Rear fuselage mounting simplifies some issues, no wing interference, easier ground clearance, but creates others. The structural weight of mounting large, heavy engines on the tail is substantial, and center of gravity management becomes more complex when stretching or shrinking the fuselage for different airframe variants. This limits design flexibility compared to underwing-engined airliners. Think of the Boeing 737 and how it was adapted and changed from the first variant over the years. I'd argue that if it wasn't possible to do that, it would not have been very successful. And that is a key design consideration these days. But even with underwing mounting, there's growing concern that open fan engines will require purpose-built airframes rather than retrofitting on existing turbofan aircraft. Any inability to retrofit represents major risk to widespread adoption. By combining anti-swirl vanes, aggressive blade sweep and variable pitch blades, open fan engines exceed turbofan efficiency by a significant margin. So if they're so great, why don't all airliners use them? Well, there has been substantial challenges. During the 1970s oil crisis, improving aviation fuel efficiency became critical. So NASA created the Advanced Turboprop project to develop high-speed Propfan technology. By the 1980s, the program successfully demonstrated 15% fuel burn reduction compared to contemporary turbofans. However, unresolved structural and noise issues combined with falling oil prices killed commercial interest, and development efforts shifted back to incremental turbofan improvements. By the early 2000s, rising fuel prices and environmental concerns renewed interest in open fan engines. But the goalposts had shifted as turbofans had become more efficient and noise tolerance had dropped to near zero. The 1980s designs couldn't simply be dusted off. They needed a technological leap. Advanced aerodynamic software and composite materials made that leap possible. Noise remains a challenge though. While modern designs meet certification requirements and approach turbofan quietness levels during cruise, they become significantly louder at high power settings and high angles of attack, conditions typically encountered when departing at maximum takeoff weight. So whether production engines will meet promised noise levels remains to be seen. Another hurdle is public perception. Many passengers distrust propeller aircraft, associating them with older or smaller planes. Blade separation events are rare and are less common than many other failures, and certification standards are rigorous. But overcoming this perception barrier will be a real challenge. Despite these obstacles, CFM International, a General Electric and Safran partnership, is pushing forward with their RISE open fan engine. Interestingly, while 1980s designs favored Contra rotating configurations, CFM has chosen single rotor with anti-swirl vanes, likely for reduced noise and mechanical simplicity. It's worth noting that one open fan engine did reach production in the 1980s with the Soviet Progress D-27 powering the Antonov AN-70. However, its 1980s technology doesn't represent modern open fan technology. The AN-70's cruise speed of around 400 knots falls short of modern airliner performance, partly because it was optimized for short and rough field operations rather than for high-speed cruise. Even so, it does exceed the traditional Mach 0.5 efficient propeller operation barrier. Whether open fan technology will finally enter widespread commercial service remains uncertain, but the potential efficiency gains make it a very promising development. I hope you found this deep dive into Propfan technology informative. Let me know your thoughts in the comments and feel free to suggest future video topics. This one came primarily from viewer requests. Thanks for watching. See you in the next one.